Okay, the final push. So we got 22 practice problems. Number one, it's a little bit different than your printout. I think I got two different tests. But I think this might be the only one. So here we go. Identify which type of sampling is used. Hopefully you studied up on random, stratified, systematic, cluster convenience. So we've got, let's see, 49, 34, 48 students are selected from the sophomore junior class with blah 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 blah. Okay, this one's going to be stratified. So if you randomly interview 49 of the 496, 34 of the 348, and 48 of the 481. So you divide them into groups, divide them into strata, and then you have to randomly sample a proportionate amount from each strata. So here we interview 0.0987% of the population. Here we did 0.0977%. On this one we did 0.0997, and they are almost all 10%. You hit 10% of the population. 49, 34, 48. So that one's stratified. B, a market researcher selects 500 people from each of 10 cities. Okay, it's not systematic. Cluster, you divide them into clusters, but then you randomly choose a cluster and you have to interview every single person in that cluster. So this one is, B is just an example of a random sample. So you hit 500 people from each of the 10 cities, doesn't really matter how big or small they are. Okay, number 2. Identify each number as continuous or discrete. Continuous is measurable, discrete is countable. A, the average height, that is measurable, so that is continuous. The number of stories in a Manhattan building, that's countable, that is discrete. Number 3, okay, the levels of measurement. Nominal, ordinal, interval, ratio. So nominal is qualitative data. Quantitative data is stuff like you can count. Can be discrete or continuous. Nominal though, nominal is just like hair color, characteristics like that. So a movie ratings on a scale of 1 to 10, that is going to be ordinal. So ordinal, you can rank them from least to greatest. Interval and ratio. Interval is kind of tricky. Interval, you can measure the difference between them, but there is no ultimate zero. There's no starting point. So interval is for like temperature, time. I mean, there's no zero time. Years, maybe. So 2018, I mean, who knows when the 0 year of the Earth was. And then ratio is, this one's the best. There is an absolute 0. So I can measure the distance from my house to the park. Starting my house, we'll call that 0. I go 2 blocks or whatever. So ratio, there is a starting point. Okay, so B, ages of the survey respondents. So you do a random survey. You record their age. Now on the test I would do this. You've got to communicate your answer, because if you can justify your reasoning, they'll give you credit for it. So B, for age of a human being, I would probably say that is interval, because there is debate on when 0, what is age 0? Is that the moment you're born? I mean, your birthday is 1 year later after the day of your birth. So is the moment you're born, is that when you're age 0? Or when you have a heartbeat in your mom's womb, is that age 0? I don't know what age 0 is on a baby. Is it the day you're conceived? The egg gets fertilized. I mean, who knows? Who knows what age 0 is? So, but if you if it's common knowledge that your age 0 is at birth, then if I can measure from 0, so 34 years old, I guess it kind of makes sense to measure from the day you're born, but I mean, you can get way picky on this one. So age could be kind of tricky. Okay, 4. Determine whether the following is a statistic or a parameter. Okay, parameter is some number that describes the population. Statistic is some number that describes a sample. And we do sampling to predict kind of qualities of the population. Because population sometimes is millions and millions of people, and it's too hard to talk with each individual personally, so we just do a sample. If it's large enough, it's going to give us a good picture of how the population behaves. So a health and fitness club surveys 40 randomly selected members and found that the average weight of those surveyed was 157 pounds. Okay, that is a statistic, because that number, that average weight, 157, that is describing 40 random people from that sample. So it's not describing everyone in the population, just that sample. Okay. Number 5. Dun, dun, dun. Just about a quarter of the way done. Frank's Furniture employees earned the following amounts last week. What was the mean? Okay, let's maybe say that's a calculator. That's all done on the calculator. So I'm just going to assume you know how to do that on the calculator. We'll do one of them, but I don't want to do this one. Mean, median, and modes. Okay, mode, you got to remember that's the one that appears most often. So 713, 713, that appears twice. That's a mode. You can have more than one mode. You can have 2 modes or 3 modes. But that one looks like it is the mode. And when you're doing a normal curve, this mean right here is also the median and the mode. All 3 of them line up right here in the very dead center. So that's something to keep in mind. Okay, this is the one I want to do. So the manager of an electrical supply store measured the diameters of the rolls of wire in the inventory. The diameters are listed below. Compute the standard deviation. Okay, so let me look at my paper. So we are going to turn your calculator on, start a brand new document, and I'm going to insert a list. You gotta name your list. So name it roll. Then you gotta punch them in. You gotta double check your data entry. Because if you make a stupid mistake, it'll come back to haunt you like I did right here. 0.111. 0.319. 479. 0.338. 0.595. 0.252. Whoops. Okay. Alright, now here we go. You go over anywhere. If you hit menu, stats, and this is just our simple very beginning. We're just going to do a stat calculation, and we are going to do one variable stats. Okay. What list do I want to look? I want to look at the roll, and here we go. Okay, so there is, well, there's all our data. X bar, that's the sample average. The sum, sigma, the sum of all my probabilities is 2.3. So it could not be a probability distribution because the sum of all those outcomes have to be 1. SX, that's the sample standard deviation, and sigma, that's the population. So they're using the sample standard deviation to kind of predict the population, and it's always going to be a little bit lower. Again, there are 6 entries. The min. Okay, quartile 1, that's the first 25%. Median is quartile 2. And then we got quartile 3, the max. Okay, so there's all your information, and then it might be handy to have this in your notes. Variance, sometimes we talk about variance. I think they put this on a test. Variance, all you do is take sigma and square it. So sigma is the square root of the variance. So if you know sigma, just square it, and that is your variance. Okay. Stem and leaf. I think we did stem and leaf. Stem and leaf looks like this. So you'd probably organize your data from least to greatest. Looks like the smallest one is, these are all test scores, so 60s, 70s, 80s, 90s, so 60s. What do I got? I've got a 65, comma, I've got a 68, tunk tunk. Then we go into the 70s, I've got a 72, comma, and so forth and so forth and so forth. So stem and leaf, not too bad. Okay, what are the 2 requirements for a probability distribution? This was on a test. Number 1, the probabilities must be between 0 and 1, each one. And the sum, this is number 2, they must sum to 100%. You've got to sum to 1. But each outcome has got to fall between somewhere 0 and 1. And they can be inclusive. Can be 0, can be 1, or anywhere in between. Okay, number 10. A car dealer is deciding what kinds of vehicles he should order from the factory. He looks at his sales report. Construct a Pareto chart. We maybe talked about that barely. Pareto chart is just a bar graph. So the sales always start at 0. Always start at 0. And I got to max out at 35, so I'm just going to count by 5s. 5, 10, 15, 20, 25, 30, 35. Okay, now you can put them, I think they like them biggest to smallest, probably doesn't matter. So the families clear up at 35. Then the truck, boom, 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 that's at 30. So each guy has his own bar, so you kind of get the feel for it. The economy's at 20, etc., etc. Okay, this one I would probably guarantee is going to be on the test. Calculate some z-score. You've got this in your note cards. To calculate a z-score, it's pretty slick. You are going to take that value they give you. You're going to subtract mu, and you're going to divide by sigma. So find the z-score for a body temperature of 99.9 K. That's what they're giving you. That is the data value. Ching. The average human body temp is 98.2, so you're just going to go 99.9, subtract the mean, 98.2, and you're dividing that by sigma. Standard deviation is 0.62. So you do that on your calculator, hit enter, and you should get a z-score of 2.74. Now that means this. And it's positive, so we're going to go to the right. 1 standard deviation, 2 standard deviations, 3 standard deviations. Boom. So it's living like right here. So this is pretty close to an outlier. It's pretty close to the top percent. Consider it to be unusual, anything that's outside of 2 standard deviations. And this is almost to the 3rd standard deviation. So this is where like the rich of the rich of the rich of the rich live. So not very many people here. You got to remember all these. 34% live here, blah, 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 blah. So not many people live right here. Most everybody lives close to the median. Right to the dead center, close to the mean. So that would be unusual, yes. Answer the following. Consider an event to be unusual if the probability is less than 5% or equal to. Roll a 12 when a pair of dice is rolled. Hopefully you've got that memorized. There's only one outcome out of 36. 1 out of 36 is 0.027, so it's almost 3%. So it's definitely less than 5, so that's yes, that is unusual. A study of 500 randomly selected school bus routes showed that 478 arrived on time. So 478 out of 500, that's pretty good. Let's see, that is 95.6%. So the chance of it to arrive late is 0.044, and that is less, so it is also unusual. Okay, so now we're getting into the good stuff. So the rest of these kind of heavy duty stats. So far it's been kind of child's play. Now 13, a random sample of 118 light bulbs had a mean life of 449 hours with a standard deviation of 33 hours. Construct a 90% confidence interval for the mean life mu. Okay, so this is kind of tricky. Now, the big question is, are we going to use a z-test or are we going to use a t-test? You use a z-test when you know sigma, which is the population standard deviation. Use the t-test when we know just the sample standard deviation. Now they're using this symbol, but that symbol, that's not referring to the population. That's referring to this random sample of 118 bulbs. So I wish they wouldn't use that. I wish they'd use something else. That's how I interpret it anyway. So a random sample of 118 bulbs had a mean life, because see, there's a huge difference between mu versus x bar and sigma versus, these are both population, so these are both parameters, and these are both samples, these are both statistics, but they're using a statistic and then they throw this sigma in, but I don't know. So on my test I would say, if you did this, you would cover your butt and guarantee you would not miss it. So you would do this. I am going to choose a t-test. I interpret this guy right here to refer to the sample, not the population. And then from here on out, you're in good shape. So if we do a t-test, here we go. Okay, I'm gonna go over here, and we're gonna go menu 6. Okay, now let me look real quick. Okay, we're doing confidence interval, so we're gonna go to 6, and I'm gonna do a t interval, and I've got my own stats. So here we go. X bar is 449. See, they're using it here, that's correct. The sample standard deviation is 33. N, how many people were sampled? 118. Confidence level, we want a 90%. Okay, then hit OK. And then there's all your data. And they're going to ask you interpret your results. So here's my results. Because of our 90% confidence interval, I am 90% positive, certain is a better word, that the true population mean is somewhere here. So my average was, what was my average? Average was 449. Now my measure of error, your give or take, was 5.03. So that means you're going to go 5.03 above, which is going to put you at 80.58, and you're going to go 5.03 below, which puts you at 71.42. So you are 90% sure that the population mean falls somewhere in this range. This is your lower limit, this is your upper limit, somewhere in there. Okay, 14. I think it's the same as 13. I don't think there's anything different except for now you're doing a 99% confidence interval. And again, see, 14's better because they just come out and say standard deviation. So 30 randomly selected students took a calc final. The sample average was 76 and the standard deviation was 9.1. And we're assuming that is, they should throw one more word, the sample. So when we only know stuff about the sample, use a t-test. You use a z-test when you know standard deviation of the population. So we're assuming everything's to the sample, so you use a t-test again. Except for this time, do a 99% confidence interval instead of a 90. And 15, a sociologist develops a test to measure attitudes about public transportation. 27 randomly selected subjects are given the test. Their average score is 76.2. Their standard deviation is 21.4. Man, I don't know, it's the same as 14 and 13. So, carry on, t-test. Okay, 16. I like this one. This one's probably going to show up. This one's hard. Use the margin of error of 133 bucks. Confidence level of 99%. Standard deviation of 533 to find the minimum sample size. So how many people are you going to have to talk to in order to really get a true estimate of this population mean? Okay, so here we go. There's a formula. N, to find n, you take your z-score squared times sigma squared, divide that by your error-bound margin squared. And we have two of the three. N equals, we don't know the z-score, but we do know sigma is 533 squared, and we do know our margin of error is 133 squared. So all we need is a z-score, and this is the key to the z-score. So here we go. They want your mean right here, and they want to be 99% sure, so that is almost everybody. Boom, 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 boom. Excuse me. Okay, 99%. Now, your tails. That means this is 0.005%. So this is alpha. Alpha is 1%. And if I split alpha up into two tails, okay, 5%. No. Half of 1%, not 5%. So this is what I need. I need the z-score of 0.5%. So to do that, it's pretty easy actually. So your Z table, your mean is always 0. And we are going to count always by ones. That's -1, -2, -3. Now the question is, I want to know, where does a 0.5% lie? And I'm assuming it's, before we do anything, a 0.5%, you assume it's going to be pretty close to the tail. Somewhere maybe beyond the third standard deviation, maybe between the second and third. So here we go. We're going to go menu. 6. And it's a distribution. It's a normal distribution, but I know the area. I just don't know the z-score. So the area I want under that is 0.005. The mean, leave it alone, hit OK, and there is your z-score. -2.6, which is pretty reasonable. We thought it would be way out there. So that means this, z equals -2.57, so that is 2.5, like right here. Bonk. So from here on is 0.5%. So now I gotta go back, plug it in. You know what z is. You're gonna plug in -2.57 squared, blah 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 blah. Do it on your calculator, and you get whatever you get. Okay, here we go. 17. A cereal company claims that the mean weight of the cereal in its packets is at least 14%. The weights of the cereal in a random sample of 8 of its packets are listed below. At the 1% significance, we're going to test the claim. The claim that the mean weight is 14, or is at least 14. So this is a hypothesis test. We're going to do a ho and a ha, and you got to remember, the ho, this is always equals, and we're talking about means or proportions. We're talking about means, so we're going to go mu, and this is always some kind of equals. Gosh, usually the claim is what you're, that's the new stuff. The ho is the old existing knowledge, and maybe the claim is something that's changed. But the claim is 14 ounces. That would be mu equals 14. So this would be, but I don't know, why did they use at least here? So if they say it's at least 14, that means it could be greater than. So let's do this, I guess. We'll use this. So it's at least 14, that means it can be greater than or equal to, and on the test I would just draw maybe an arrow to that. So they're kind of giving you two different things here. So that means the claim is that it's, we think they're screwing us. We think it's actually less than 14 ounces. Okay, so now on your calculator, I'd probably just do a new document. Don't save any changes. We're going to add a list. Ounces, we'll name it, and now we got to punch them in. 14.6, 13.8, 14.1, 13.7, 14, 14.4, 13.6, 14.7. They're not giving you very many entries. We got 8 entries here. Double check them. 14.6, 13.8, 14.1, 13.7, 14, 14.4, 13.6. Okay. So you double check, and now you come over. You can even stay in this menu. We're going to go menu, stats. We're doing a stat test. And we are doing, okay. Are we doing a Z test? Are we doing a T test? What are we doing? Z, you gotta know some stuff about the population. We do not. Okay, so here we go. We're going to do a t-test. And we're going to do it on data that we have collected. Hit OK. Okay, the mean of the null, they think it is 14 ounces. On the list, we're going to go ounces, the frequency. Okay, now the alternative hypothesis, we're saying, what did we say? That the alternative is less than the null. So we're saying the null is at least 14, so 14 or greater, so the alternative is going to be less. And this is what Haley discovered. You can have it draw. Hit OK. Now, so we got our p-value. Oh, where's all my stuff? I guess it's just right here. Oh, I guess all I really need is the p-value. So let's look. Let's do it on your calculator. So if I go home and I enter a graph, now let's do the same thing. Let's go menu 6. If we do a stat test, we're going to do a t-test, exact same thing from the data we've collected. Hit OK. That's 14, and this is ounces, and we went this way. Hit OK. Okay, there's all the stuff. So t-value, a p-value, x bar. Oh, so this is the sample. Yeah, the sample average was 14.05, which is a little more than their claim. So the p-value is pretty freaking high. So here we go. Dun dun dun. Now if I go back and look at this, yeah, it does. I guess it gives me everything. The t-score, the p-value, 0.6. So we need that 0.65. So here we go. So your p-value equals 0.65, and we're testing at the 1% significance. So that means my alpha is 0.01, and you just got to memorize this. When alpha is greater than the p-value, then you reject the null. So it turns out that my alpha is way less than my p-value. So that means I gotta go back to the drawing board. There is not enough evidence to conclude that I need to reject the null. So I probably gotta increase my sample size. I gotta do something. So we are not rejecting the null just yet. Okay, 18. Okay, now this is what we just barely did right before you guys went to Lagoon. Okay, 7 of 8,500 people were vaccinated against a certain disease. They later developed the disease. 18 of 10,000 people were vaccinated with a placebo, and they later on developed the disease. Test the claim. So our ho and our ha, that the vaccine is effective. So this is the claim. This is what we are suggesting. Okay, so, but here's what you're doing. You have two things going on. You have a vaccine versus a placebo. Okay, there's a huge difference. So we were comparing the average to a target number, to 14 ounces. We are comparing, now this is not an average, this is a proportion. So vaccine, 7 out of 8,500 people got it, that's a percent, so it's a proportion. Placebo, 18 out of 10,000 got it. So, I mean, 8,500 is pretty close to 10,000, and 18 is more than doubled. 7. So it kind of looks like the vaccine worked. So that's our claim. The claim is the vaccine worked. So here we go. Now, the ha is this. The proportion that the vaccine, the percent of the vaccine, so these people have the disease, got sick, is less than the proportion of the placebo who got sick. And so your ho is going to be opposite. Vaccine is greater than or equal to, this always has to be inclusive, popular proportion of the placebo. Okay, now here we go. Now this is called a two-sample test. We're comparing two samples, those who got vaccinated, those who got the placebo. So you go on your calculator, and I'm going to do it from this screen. We're going to go menu 6, 7, and that is a two-sample proportion. Alright, now your successes, and if I go back one, whoops, there was no statistics, 7, there's no t-test. I kind of want to do like a t-test instead of a z-test, because z-test is population. But we're just looking at samples, but there is none, so let's just, I don't freaking know, let's use the z-test, because that's all there is. So, one we're going to call the vaccination. So the successes, how many were there? Where are we? 7 out of 8,500. Then the next one, there were 18 out of 10 grand. And we think that the alternative is greater. No. What do we put for the ha? Okay, so the first one is smaller than the second. So the first one, I gotta change that, I gotta go here. First one is smaller than the second, hit OK. And there we go. Okay, here's our p-value. Our p-value, that's what we're after. So the p-value is 0.036. P-value equals 0.036. Now most of the time they're going to use a significance level of 5%, but this time they ramped it up a little bit. So we're going to go 2%. Now, alpha is less than 0.036. Alpha is less than the p-value. So it's only when alpha is greater than the p-value that we're going to reject. So we're going to conclude there's not enough evidence to suggest that we reject the null just yet. So we got to go back to the drawing board. We can, if we said alpha was 5% at the 5% significance level, then we could say, yep, we're going to reject the null. The vaccine is working. Okay, 20. Okay, now these ones, this is chapter 12. 20, let's look at A. You've got to use this chart right here. So N is 25. Your correlation coefficient is 0.539. You've got to use this guy right here. So you come on this chart and they'll give this to you on the test. What was N? 25. So that means you come over here Ooh. Okay, now look. You have to because there's two variables, there's some on the x, some on the y, you got to take your degrees of freedom and you've got to subtract 2. So my n was 25. That means my degrees of freedom are going to be 25 minus 2. So I need to look at 23. That might mess you up. Okay, let's go 23. Okay, 23, I'm looking at 0.396. So here we go. That means 0.396 this way, negative 0.396 this way. So there is my window. Okay, now your correlation coefficient is 0.539, so it is, you gotta remember this. So it's right here, this is my R value. And if the closer you get to 1, that means the stronger the relationship is. 0 has no relationship. So I want to be outside. If I'm outside of this window, then yes, the answer is yes. And it's always defaulted at a significance level of 5%. That's always the default on these. So the answer is yes, there is a strong correlation between whatever those values were. As long as I lie outside this box, the closer I get to 1, yes, they are strongly correlated. Okay, B, let's go 0. Now you've got n is 15, so my degrees of freedom are going to be 15 minus 2, so that's 13. So I come over here on 13, 0.514. Okay, that means I'm going to go 0.514. So I guess clear out here is 1. Clear out here is negative 1. So negative 0.514. Boom. And my R value is 0.359. So my R value lies within this window. So there is nope, not a strong enough relationship. So they're not strongly correlated. Okay, let's try 21. Now, 21 we're going to do our own. Two different tests are designed to measure employee productivity and dexterity. Several employees are randomly selected and tested, and here are their results. Use the data to find an equation of the regression line. Round the values to 3 significant digits. So we have got, okay, I'm going to probably have to do a new document. Don't save the changes. Let's go here. So I'll do P for productivity and D for dexterity. And I'm just going to do a couple. 23, 25, 28, 21, well, I guess it doesn't take long. But I'm not going to double check them. 49, 53, 59, 42, 47, 53, 55. Okay. Now I'm going to come over here. I'm going to go into my menu. Stats. Let's do a stat test. Now let's come into here. Let's try a linear regression t-test. Alright. My X list, I want productivity. I guess it doesn't matter. It's not going to matter which, because there's not an independent variable here. So what I mean by that is, does the productivity depend on your dexterity? Or does the dexterity depend on your productivity? So I guess since they give you the table, we'll call the productivity the X, and we'll call the dexterity the Y. And we're good. Don't hit OK. Okay, now you have all sorts of stuff. So there's the title. Okay, your regression equation is a plus bx, so a is your y-intercept and b is actually your slope. I got a p-value. So my p-value is 0.1. Dude, your p-value is... Oh, no. If I hover over it, okay, because I say your p-value is like 100%, 159%. That's no good. So your p-value is actually way small because this e to the negative 7 means you're going to move your decimal 7 places to the left. So alpha is, if alpha is 5%, alpha is going to be way bigger than your p-value, so you are going to reject the null. Okay, so here's what that means. They didn't even ask you to do any of this, but this is good. So your null is always defaulted that that the correlation is 0. So the ha is that it is not 0. So if it is 0, there is no relationship. What do we call that? What did we call that? Test. That's where I want to look. Okay, so this is where it was in our 12.4 lesson. Oh, they're just going to call it a population correlation. Okay, so you default saying the null is that there is no relationship. And if you reject it, then that means there is going to be a relationship. And that's what we're going to do, because I don't even know where I am now. Here we are. So alpha, we'll say that's 5%, and your p-value is way small, blah blah blah. So alpha is greater than your p-value, so we're going to reject the null. That means, man, there is some kind of relationship between productivity and dexterity. So the more productive you are, the higher your dexterity, maybe, who knows. Yeah, 36 is higher than 23, and 75 is way higher than 49. So anyway, your regression line is going to be y equals a, and a, I gotta go down, a is 5.05 plus, that's your slope, so they're positively correlated, 1.905x. Okay, 22. We're almost done. So 8 pairs of data yield a correlation coefficient of 0.708, and the regression equation, blah 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 blah. Also, blah 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 blah. What is the best predicted value of y when x is 4? So let's just plug x as 4. So go 2.79 times 4 plus 555.8, and that will give you y. Sounds pretty easy. Just take that value, plug it in for x, do the arithmetic, and that will predict a y. So like our dexterity. So if I have a dexterity level, they just want me to predict. So I've got this equation that relates my productivity to my dexterity. If I know my dexterity number, let's plug it in. Actually, this one would be x was your productivity and y was your dexterity. So if I know my productivity level, whatever they measured, if I know it's 50, boom, plug it in, times by 5, add 2, 5 there, give me 5. So if I take 5 and times by 5, 25 plus 2, that's 27. That means my dexterity level would be 27. That's it.